10.3, we're going to talk about the difference between independent and dependent events today. So with independent events, basically the outcomes don't affect each other. So no matter what has happened beforehand, the probability is still going to be the same. So for example, something like flipping a coin, like spinning a spinner, and we'll do an example question here where we can find the probability of getting 4 heads. So the probability of getting a heads the first time, so I know toss 1 is going to be 1/2. Well, toss 2 is still 1/2. 3 is still 1/2. Whoops. Toss 4 is still 1/2. And so I can just multiply all of those together, and I get 1/16 as my probability. So those are independent because even though I might have gotten heads on the first toss, I still have an equal chance of getting heads on the second toss. It doesn't change just based on what happened beforehand. So that's the difference between independent and dependent events. So one outcome is going to affect another probability. So an example with this would be like drawing cards from a deck. Or maybe picking members of a committee. And here's what I mean by that. Here's an example. So let's say all right, let's take a look at the probability if I'm drawing 2 hearts and 1 diamond from a deck of cards. Some of you know about a deck of cards. There are 52 cards and there are 13 per suit. And so my first card, let's say go for a heart here. Well, I know there are 13 hearts out of 52 cards in the deck. Well, my second card, assuming that I drew a heart the first time, well, I don't put it back, so that means there are only 12 hearts now, and that also means there are only 51 cards in the deck. So you see how that probability changed based on what happened before it. That's what makes this a dependent event. For the third card as a diamond, well, there are 13 diamonds, but because I drew a card, there are still only 50 cards in the deck. So this is why we have a bunch of different probabilities and why it's a dependent event, because the big key here is that this probability with coins stayed the same no matter what. But these probabilities with the cards changed every time. And so if you were to type that in your calculator, you would get 13 out of, I think, 850. Great. So those are the big differences between independent and dependent events, and now we're going to do some examples with that. So first thing, There are two properties that happen with independent events. One of them is that the probability of an event happening, of both events happening, is their individual probabilities multiplied together. Let's look at this with the drawing cards example. So, our rule, probability of A and B is probability of A times probability of B. Well, with flipping a coin, let's say getting a heads, getting a tails. Well, it was 1/2 times another 1/2, which gave us the full probability. That is correct. But if I was drawing a card, so let's say, the probability of getting a heart, wow, that was a really terrible heart. I'm going to do that again. The probability of drawing a heart is 1/4. The probability of getting a diamond is 1/4. But when I drew the cards out of the deck, that 13 out of 52, but now it's 13 out of 51 because I drew a card out of the deck. And so because it changed, that means that they're not independent. So that's what that part is meaning. The second characteristic is that the probability of A given B is the same as the probability of A. Let's translate this into what the heck does that mean? Well, this means the probability of A given a condition. So let's say the probability that I flip a heads, given that I just flip tails, does it change from 1/2? No, it does not. This means no matter what has happened beforehand, the probability is still the same. Or no matter what condition is placed upon event A is still going to maintain that same probability of happening. That is what that means. So with this, let's look at our first example. Let's say the probability of event A is 3/4 and the probability of event B is 11/20, and we need to find the probability of A and B. Well, because I know they're independent, then that means the probability of both of them happening is their individual probabilities multiplied together. So that's going to be 3 out of 4 times 11/20, which gets us 33 out of 80, and that does not reduce. Let's say we have probability of event A is 5/7. The probability of event B, here, let's actually do the probability of A and B is 3/4. And we want to find the probability of event B. Well, this I can kind of set up an equation going back to my first equation that I have in the box. I know that 3/4 has to equal event A times event B, which means to get both sides by itself, I can just divide both sides by the 5/7, because those will cancel. And so I know probability of B is 3/4 divided by 5/7. Well, just a reminder, dividing fractions is the same as flipping and multiplying. So you get 21 out of 20, which isn't possible because it's over 1, so that was my bad for picking crap numbers, but you get the point. That's what you would do there. Never try to make up math in your head, it's fine. Okay, last example, let's say probability of A is 5/7. Here we go. Probability of B is 3/4. So I want the probability of B given A. Well, if these are independent, probability of A given B is the same as the probability of A, meaning no matter what condition is placed on your event, the probability remains the same. So if I'm looking at probability of B given A, and they're independent, well, it's just going to be the same as the probability of B, which is going to be 3/4. All right, let's apply this now to two-way tables. And we're just gonna make up some stuff. All right, let's say we take a survey and we have 5 boys prefer cats and 9 boys prefer dogs. And then we have, I don't know, 8 girls who prefer cats and 13 girls who prefer dogs. I'm going to change that so the numbers aren't so similar. Let's make that, oops, 12 and 20. I was wrong in my math anyway. It's fine. 9 plus 12 is 21. So really I just made my math work out better. It's fine. Anyway, moving on. Let's say, just a quick refresher here. I want the probability that someone is a girl given they prefer cats. Well, reminder from last time, if I'm looking at that given probability, that means I'm looking for, okay, how many of the girls preferred cats? So out of all the people who preferred cats, sorry, how many of the cat people are girls? So it should be 8 out of 13. Next question, is being a girl independent of liking cats? Well, at first glance we'll say, well, yeah, it doesn't really matter. But if 2 events are independent, then this rule should be followed. So I can just test that. This means that the probability of a girl preferring cats should be the same as just picking a girl at random. And if these are truly independent events, those probabilities will be the same. So we already calculated this one to be 8 out of 13. Well, the probability of picking a girl is 20 out of 35. And I can see that those are not the same. So these are not independent events. Interesting, isn't it? This is where you start to find subtle biases and things like that. Okay, the only other thing that I want to bring up would be a formula. Going along with this idea of how we found what's in green. Okay, the reason I color-coded this in green is because it's exactly the same thing that we did in green on number 2. Where this thing, the probability of A given B is the probability of A and B over the probability of B. Well, if we look at that, the intersection is what I circled here. That's the 8. So that's the intersection of girl and cat, and then out of the category of B, which was cat, so out of that 13. And so I bring up this formula because now you can use it to find other probabilities, like that's the last 4 questions on your homework. But the big thing I want you to know is that you're already doing this. But now you have a formula to use and to get things by itself, kind of like we showed in number 1. And that is 10.3.